Hello, everybody. My name is Patrick Wheeler. I am responsible for product management of Oracle Multitenant, and that's the subject of today's session. The title of this session today is Best Practices for Rapid Deployment and Workload Isolation. And the format is that we've got about an hour together here, and I'll speak for about 45 minutes with slides, and that'll leave a little bit of time at the end for Q&A. And we're using a Zoom webinar here, and you'll see that you have a Q&A button which is enabled. And if you have questions during the session, I'd encourage you please to use that. We've got a number of experts on the line here with me who might be able to answer those questions on the way through. And then at the end, we may have some that I'll take live at the end of the session. But let's get started here. Best practices for rapid deployment and workload isolation. So that title's made me think quite a lot about how I might approach this topic. And I could be rather glib here, and I could say the best practices, if you go to the cloud, or you use a private cloud. And I think given the audience we're talking about here, I suppose most people would be thinking about using a private cloud for this. But while we're on the topic of cloud, a very good example of how to get rapid deployment with workload isolation is an Oracle Cloud. It's Oracle Autonomous Database, which incidentally is built on the multi-tenant database architecture. In fact, when you provision an autonomous database, you're provisioning a pluggable database. So bear that in mind. And if you want a very, very good example of how we deploy very rapidly and provide workload isolation, just dig around with autonomous database. There's an always free tier for that. I strongly encourage you to look at that, look at the simplicity of the provisioning framework, and think of that as a model. If you want to deploy your own private cloud, think of that as a model of how you would build an orchestration framework that would sit behind this sort of thing. So the glib answer to this, what's the best practice? Well, the best practice is to deploy a private cloud framework based on multi-tenant. And now let's sort of get to the details of this. First of all, what are the requirements of the database cloud? And then we get to a phrase which I suppose is a bit of a scramble of our title here: isolation and agility with economies of scale. And it's the economies of scale part that I think is the reason why a lot of people are moving to a cloud framework. Because it all comes down to economics, doesn't it? It's all about cost. And the cloud affords us great economic advantages, as well as some agility advantages. But there's no point in moving to something which potentially saves you money and allows you to do things faster if all of that comes at the expense of isolation. So that's why I think it's very important to talk about all of these topics at the same time. And I'm going to cover all of this. And in fact, what I'll do as we go through this session is to break that phrase down and talk about them in reverse order. So I'll talk about the economies of scale. That's the big raison d'etre, if you would. Why are we doing this? Because of the economies of scale, because of the agility. And then we'll get to this all-important topic of isolation. And then I think we're going to have a little bit of time at the end to talk about how you might upgrade to multi-tenant. By that stage, I hope to have convinced you it's a very good idea. And be aware that many customers have gone before you and they're already happily using multi-tenant very successfully. So we can talk very briefly about some use cases and customer successes. And it's worth noting that this is not a new architecture anymore. It was released in, I think it was June the 23rd, 2013. So it's been 8 years, more than 8 years of experience we have with multi-tenant now. Okay, so let's jump into the requirements of database cloud. And these are really the business drivers that push people towards a cloud-based environment, a public cloud-based environment, or a private cloud-based environment. And in general, we have business pressures, business drivers, in two categories. There's the economic pressures and the operational pressures. On the economic side, it's all about money. You're consolidating to cut costs. You cut costs by consolidating. So you can do more with less, or you can do the same amount with considerably less. In general, one expects business to grow, so you have to do more with less, or at least with a great deal more within the constraints you're currently in. So for a given workload or set of workloads, you want to be able to handle that with fewer servers, consuming less power, using less floor space in your data center. Quite often, a rough metric of how much things cost is how many floor tiles do you occupy in your data center, literally. All of this translates to reducing license costs, which is very important. It's a very important consideration economically. On the operational side, we're all familiar with the cloud now, whether we're using it at work or not. Cloud-based agility means simplified management, self-service provisioning. You don't want to have to do things through SRs anymore. And you want to be able to have a great deal of flexibility, flexibly adjust to changing workloads. That's a key requirement. So we've got these two big categories, economic and operational, and various requirements. And I've listed those in the middle here. We need to be able to handle all this stuff. We need to handle tenant isolation in this consolidated environment. It's a new architecture, but it's got to be easy to adopt. As I go through this list, you see, it's somewhat self-contradictory, right? So we've got a new architecture, but it's got to be easy to adopt. We're going to consolidate so that we can manage many as one. That gets us efficiency, but we want to retain granular control. And while we manage many as one, we want tenant isolation. So you've got this potentially contradictory set of requirements. How do we thread that needle? So going back many years ago, when we were deciding what was the right architecture for the database cloud, of course, we considered what was currently available. And at that time, a decade or so ago, that was the dawn of these massive consolidated systems, engineered systems, for example, Exadata from Oracle. And these things are very, very powerful, and they have the capability of storing many databases just piled in there. But it's not a very good model because the databases weren't really designed to coexist with each other. It's not particularly efficient at all. Basically, the power of the machine is masking the inefficiency of that model. So an obvious place to go from there, maybe thinking back a decade or so ago, would be to consider replacing each of those individual standalone databases with a virtual machine running a copy of the Oracle database in it. Maybe a more modern way of doing this would be to consider using Docker containers with each container running an Oracle database in it. But whether it's virtual machines or whether it's Docker containers, it's not a particularly good way of consolidating these databases together. Yes, you get some pretty good isolation and agility, particularly good with the VMs. They can be provisioned pretty quickly. The isolation's good. But the efficiency is not good. And the efficiency is not good because in each of these little VMs or Docker containers, you've replicated the entire stack of Oracle software. And in the case of the VM, you've also replicated the operating system stack as well. And that is that's a pretty solid, pretty heavy stack of software to replicate again and again and again. So this redundant replication of overheads is particularly inefficient, and you quickly chew up the available resources of the system there. But you get some marks for isolation and agility. Now there's another approach entirely. By the way, this little mnemonic here just tells us what's a classic, what's the sort of almost the minimum footprint of one of these VMs. This is why you chew up the resources so quickly, because how many times can you stick 6 gigs of memory into a machine before you've run out? It's just not an efficient way of doing things. So a more efficient way of doing things is very high scale consolidation within a single database. Because remember what I was saying about the problem up here, that we've replicated all of these overheads redundantly. Well, if you have a single very large database running a single copy of Linux, there's no replication of overheads there. So we've got a single SGA shared amongst all these different users. It's very, very efficient. And you've only got one database to manage. Whereas up here, you've replaced your physical sprawl with virtual sprawl, but you've still got exactly the same number of things to manage, to patch, to upgrade, all that sort of stuff. Well, down here, we've got no replication of overheads, and we've only got one database to manage. We've only got one thing to patch. We've only got one thing to back up. So it's great from the efficiency point of view. But from the point of view of isolation and agility, you've traded in all of that isolation and agility to achieve this efficiency. Let's just give some examples here. If you want to do an upgrade, then everybody upgrades. So there's no agility there particularly. Everyone has to be in lockstep. And it's a basic premise that the more you consolidate, the less likely it is that you can find a single window in which you can upgrade everybody. It becomes harder and harder to negotiate that. So that's the sort of problem you get. The next is isolation, because the database doesn't know that these workloads are supposed to be separate. It's just separated by convention. Everyone's data sloshing around in the same database. So you have some isolation challenges with that model as well. So the idea is, let's come up with a new framework, which has the best of both worlds. We want you really to have your cake and eat it, so that you can have all of the agility and isolation that we have with this VM or Docker-based model, and all of the efficiencies that come from the consolidated environment. So that was our design goal. And if we can meet this goal, we can basically deliver on all of these benefits, minimizing capital expenses and operating expenses. This was the consolidation gain. So we get this by doing this schema consolidation or row consolidation, putting everybody in a single database. But we also want to maximize agility, and we want it to be easy to adopt. Now, schema consolidation and row consolidation, that's not particularly easy to do. And as we discussed, the agility isn't great, but the idea is that multi-tenant should deliver on all four of these benefits. So in the next few slides, I'll be explaining how this is done. But again, let's spend some time first on the whys. And I talked about efficiency. So what are the technical efficiencies of multi-tenant? How do these deliver? This is the first category of economies of scale. Let's go back to the old architecture of the database before multi-tenant, and this classic or non-CDB database architecture. Think about what happens when you provision a new database. What do? Well, obviously we've got a set of files on disk to store all the data, but when we fire the database up, we've got an SGA, the system global area, the memory area in which all of this data is managed. And we've got a series of background processes that manage it all. And as you fire this up, you consume some of the resources of your system just for running the engine, if you like, before you've even carried any workload. And as you add more and more databases to your system, you can quickly overwhelm it just by running all this infrastructure before you've really even gotten around to running any workloads in there. So this is not a particularly efficient way of doing things. The idea of the multi-tenant architecture is we replace all of these formerly standalone databases with what we call a pluggable database, which is consolidated into an environment which has a single SGA, a single set of background processes, and it's far more efficient. By eliminating this redundant replication of overheads, we leave far more processing available for handling the workloads. And that's really a great source of technical efficiency. Now, I've got a bit ahead of myself there. So I want to go back and formally define some terms. I mentioned pluggable databases. And for those of you who aren't familiar with this, I'll dwell on this a little bit. Pluggable database. First, the database part. From the point of view of an application, a pluggable database is just like an old style database. It hasn't changed in any way. And that's very important because it means that an application can run unchanged in a pluggable database. That's great. So it's easy to adopt this architecture. Okay, so what about the pluggable part? That's what's new. The pluggable part means in this new architecture, we have what we now call a root database into which we plug these various pluggable databases. And this whole unit now we call a multi-tenant container database. What a mouthful that is. So we abbreviate that as CDB, CDB for container database, and PDB for pluggable database. So informally, you hear people talk about CDB, PDB, or pluggable databases. Formally, we call this the multi-tenant architecture or the container database architecture of Oracle Database. And in the current release, which is actually 21C, but 19C is our long-term release. And if you're on a prior release of Oracle, I'd encourage you to upgrade your production databases to 19C and start experimenting with some of the future capabilities that are now available in 21C. We call that our innovation release. In these latest releases, we can support up to 4,096, that's 4K, PDBs per CDB. If you're running in Exadata, or if you're running in Oracle Cloud, and if you're running in other platforms, we can support up to 252 PDBs per CDB. So very high scale consolidation is possible, and best of all in Exadata and on Oracle Cloud. Okay, so this is how we get the technical efficiencies. Basically, we eliminate redundant replication of overheads, and that allows us to consolidate more applications per server. But there's more to economies of scale than just technical efficiency. Operational efficiency is the second part. So this is economies of scale part 2. And we achieve this because we can manage many databases as one. For example, if you're doing a backup. Now remember I said that with a pluggable database, the application thinks that the PDB is the database. Now the DBA, the database administrator, thinks that the CDB is the database, the primary unit to manage. So that means that the DBA does DBA stuff to the CDB. And in this example of backup, you configure a backup at the level of the CDB, and all of the workloads are backed up in one fell swoop, which is great. So this is a great example of managing many as one. But if you want to do something granular, for example, you want to do a point-in-time recovery, we sometimes call this a PITR, point-in-time recovery at the individual pluggable database level, that's possible too. So we can manage many as one, but retain granular control. And here I'm beginning to hint at some of this agility that comes along with these technical efficiencies and these operating efficiencies. So consistent with our theme this morning. Another example of managing many as one is configuring for high availability using something like DataGuard. Now, the way we do this technically is that we have a primary container database. And because we can manage many as one, we configure DataGuard at the CDB level. And all the PDBs plugged into that CDB are protected by that single configuration. So that's very important. Technically, the way this works is that transactions that get written into a database get protected because they're written into the log file, the redo log file. Now, remember I said that in this consolidated environment, we only have one set of background processes. So we've got one log writer writing into a single consolidated redo stream. And so you set up DataGuard at the CDB level. Here's our primary container database. Here's our standby at some remote location. And this single redo stream is replicated. So all of the pluggable databases in your primary are protected by having their transactions replicated to the standby. And then if you drop in a new pluggable database in your primary, we have a corresponding one on the standby side, just by virtue of being plugged into this environment, which is already configured for high availability using DataGuard, it's automatically protected. So there's a great example of managing many as one, and indeed of agility for the example I just gave at the end there. Another example of managing many as one applies for the application administrator, not so much the database administrator. So for the application administrator, we provide what we call an application route. If you're running a SaaS operation, perhaps you're in the ISV business, perhaps you're running a global business like Oracle, where we replicate our business practices around the world. Perhaps you're running a franchise business, car dealership, or whatever it might be. You're in the SaaS game then. You want to have individual tenants for your individual businesses, but everyone runs the same application definition. So you can have a single application definition using this framework, and we call this the application container capability. So we centralize application administration, but we can still do powerful cross-franchise operations such as aggregation, etc. Another great example of managing many as one comes when you do an upgrade. Because we've only got one operating environment, and because the DBA does DBA stuff at the CDB level, you would run, therefore, an upgrade at the CDB level, and all of the databases inside it get upgraded in one fell swoop. And that's extremely efficient. It's extremely efficient when it's convenient. Now, you might remember that at the very beginning I said one of the downsides of the schema consolidation or row consolidation approach is that everybody has to do an upgrade all at once. And here I am potentially contradicting myself. Well, I'm not, because we have an alternative. So in certain use cases, and I think development is a good example of this, where you're not running a 24/7 operation. Maybe you're running a 9x5 operation. You can tell a development team, take the weekend off, guys, take the kids to the beach, or whatever you want to do. Come back on Monday, and everyone will have been upgraded. In those sorts of environments, running an in-place upgrade, as I've illustrated here, is a perfect way of doing things. It's extremely efficient. But it's not always possible to do that. And in production, it's typically difficult to find an outage which is simultaneously convenient for everybody. So we offer an alternative. And here we step into the main theme of our presentation today, or one of the main themes, which is agility. So let me give you an example of how an alternative way of doing an upgrade. So let's say that we have two container databases. We've got one at release 19.4 and an upgraded one here at release 19.7. Just pause to think about what that means. We've got an old database version 19.4. We've got a newer one here. This one has a set of binaries running at 19.4. This one has a set of binaries running at 19.7. So the binary part of the upgrade is already taken care of. Here we've got a container database with the upgraded data dictionary definitions. Basically an upgrade has two components, right? It's got the binary component, it's got the data dictionary component. These two components are already at the new version. So by simply moving a PDB from the old container database to the new database, we've already done most of the upgrade. We've got the new binaries there. We've got the new root database with the new definitions. Yes, we do have to run the upgrade in the individual PDBs as well, but because much of the upgrade has already been done, that's a significantly faster operation, and it will take significantly less time on aggregate to do this. So we've got this alternative way of doing upgrades, and notice that it's granular. Notice that this has been performed at the level of the individual databases. For whatever reason, this one, which I've labeled AP, has stuck behind at the old version. Perhaps it wasn't convenient business-wise. Perhaps there's some dependency on a third-party piece of software which isn't yet certified with the new version. I don't know. I don't really care. I just know that I can offer the ability to do a granular upgrade when appropriate. So this is a good example of agility and perhaps isolation of workloads that makes it practical to do very high-scale consolidation. It's a good example of getting our cake and eat it, as I mentioned right at the very beginning. So another example of the sort of agility that we can get with multi-tenant is with real application clusters, RAC. Now, multi-tenant makes RAC better and RAC makes multi-tenant better. And I'll run through the next few slides by building up a real application clusters environment with multi-tenant involved. Now, just that statement, building a real application clusters environment around multi-tenant, that's a sort of DBA thing. So it makes sense to be doing this at the CDB level. So for a single CDB with shared storage, which is the requirement of RAC, of course, let's start by building a cluster with just a couple of instances. So we've got instance 1 and instance 2 running on node 1 and node 2 sharing this common storage environment. And the first question then is, okay, well, where do the PDBs show up? And we call this the affinity of a PDB to a node in the rack cluster. And basically the way that the affinity of a PDB to a node in the cluster is defined is by starting its services. So here we have PDBs 1, 2, 3, and 4. I'm showing them here with these red drums. And these little gears spinning are supposed to represent the services. So by starting the services of a PDB, that's how we open it in a particular node. That's how we define its affinity. So here we have PDBs 1 and 2 with affinity to instance 1, and 3 and 4 with affinity to instance 2. Now, what happens if you look in instance 1 for PDBs 3 and 4? And in fact, they show up, but they show up in mounted state, which is basically closed. So these two are open, and these two are closed in instance 1. And conversely, in instance 2, PDBs 1 and 2 are closed, and 3 and 4 are open. And so this is really nice. It's a nicely balanced system. These little meters here are showing a pretty nicely balanced system. So we say, this is great. And we want more of that, please. That sounds very good. So we'll add a few more workloads, drop a few more PDBs in here, and maybe we'll, put one in one instance, one in the other instance. This feels like it's going to be nicely balanced. But unfortunately, these guys seem to be a bit heavy. And now you see us in the red zone here. We're in danger now of violating our performance SLA because, frankly, we've overloaded the system. What are we going to do about that? Well, how about we add another instance, another node to the cluster, and then do a little rebalancing by moving the services of perhaps the PDBs we just added to the system. And so now we've got a nicely balanced cluster again. We've got our workload spread out across, and this is, we could call this singleton affinity. You see this nicely balanced set of resource meters here. So everything is hunky-dory. Now we've got, I've shown you so far singleton affinity. We can have uniform affinity. Indeed, we can have multi-node affinity. And I'll refer back now to Autonomous Database. We do exactly this. Autonomous Database is deployed on hundreds of Exadatas around the world, but these are full racks of Exadata. So we're running 8 nodes of real application clusters in each one of these Exadatas. And if you have 16 OCPUs or more, I think you will always have at least 2 nodes. And you can go all the way up to very large numbers of CPUs, in which case you have potentially all of the nodes of the Exadata at your disposal. So multi-node affinity, we definitely use. We use this sort of load balancing all the time to keep the system nicely balanced, to continue to deliver our SLAs, both in terms of performance and availability. And indeed, this is what you can do when you deploy your own private cloud based on multi-tenant, particularly if you've built it on rack, and best of all, rack on Exadata. Okay, so moving on here, another important theme under the category of agility is when we start talking in terms of changing SLAs, service level agreements. And a typical model you'll see, we talk about this quite a lot in terms of best practices, is to use these Olympic medals, bronze, silver, gold, and some people talk about platinum as well, as tiers of service level, basically defined in terms of availability. So perhaps the bronze tier, the lowest tier, your availability is defined by backups. Perhaps you're doing weekly full backups, nightly incrementals, that sort of thing. the silver tier, you're adding RAC to the picture. So RAC, as we know, protects against instance failure. It also gives us some of the load balancing I've just been talking about. But in the top tier of availability with gold, you want both RAC to protect against instance failure and data guard to protect against media failure. Indeed, an entire data center being taken out by a fire or a flood or whatever it might be. We want data guard to protect and allow operations to resume in a remote location. So let's talk about changing SLAs. And a typical thing here, I'll give another example from Oracle Cloud. Some of our SaaS operations run on a 30-day free trial model. So you come along and somebody says, well, okay, I'm going to try this thing. Now, you get what you pay for. And 30-day free trial, we have limited SLAs, perhaps it's this sort of SLA. But what's really important for a SaaS model is what we call the conversion, when that customer says, I really like this, I'm going to start paying for the service. Now, when they pay for the service, you want to upgrade their SLA. And you think about the old world and how hard it was to take a database and say, now I have to build RAC on this thing. Oh gosh, that's quite a project. But with multi-tenant, that sort of operation is extremely easy. It's just a matter of unplugging your PDB from the lower tier CDB and plugging it into the higher tier CDB, or indeed doing a PDB relocation. And indeed, if you want to go from silver to gold, because your workload has been deemed to be very important by your business, that's simply a matter of unplug, plug. So the way to think about this is you have tiers of CDBs at these different levels, bronze, silver, and gold. And you manage the CDBs to deliver the SLAs that are required. And then what you do is you just populate the PDBs in whichever tier is appropriate for the business that they're supporting. And then changing the SLAs is just a matter of moving them around the place, as I was talking about. So this is where pluggable portability that's enabled by multi-tenant is this great enabler of business agility. In this example, changing SLAs. Now, there's another good example of agility, and maybe this is the where you thought I was going to start. I thought about starting here, actually. And that's the initial provisioning. I talked about pluggable portability just now for an existing workload, but what about a brand new workload? Well, in every CDB, we have a special little PDB, which is called seed. If you look in there, if you say show PDBs, you'll see it there. It's called PDB $seed. Always, non-negotiably, that's the name of what we call our seed database. And it's basically an empty database. Now, when you say, I want a new pluggable database, technically that's implemented by a statement that says, create pluggable database. I might call it Patrick. Create pluggable database, Patrick. That's it. That's all I write. What happens under the covers is that we take a clone, a copy of this seed database. Now, what is a pluggable database? It's basically a set of data files. You've got data files for each, for each of your table spaces, so system and sysort and users and all that sort of stuff. We literally copy all those files, and then we put a new global UID, a GUID, we call that, global UID, on top of it. And that's it. That's your new database. It's as simple as that. Copying some files and putting a new GUID on top. That's why it happens so quickly. So we've got this pre-existing database. You create a new one and it shows up in seconds. So again, go to the Autonomous Database Framework. You click provision a new autonomous database, and there it is. That's how we can do it so fast. Now you can use the same technique for copying an existing database, perhaps a production database. You might want to copy this for debugging purposes. Whatever purpose it might be, you can clone it using the same simple SQL, create pluggable database, A from B. It's simple to do. Now, this is an extremely efficient set of operations. What I'm describing here are full clones. We also have this capability we call a snapshot clone. And a snapshot clone behaves very much like a full clone, except behind the scenes, we're cheating. A snapshot clone is thin provisioned in our parlance. These are storage efficient snapshots. So the underlying data files are actually not copied. We're using sparse files. We're pointing to all the original set of data blocks. So the sparse file copy points to the existing data blocks rather than replicating them. So if you really just need the clone, you can use the snapshotting capability. It uses negligible incremental storage. And because of that, it happens extremely quickly. Even if you're taking a snapshot clone of a very large database, it can happen very, very quickly. So this is very, very efficient compared to cloning a non-CDB, creating a non-CDB using DBCA or something. It might have taken you 20 minutes or so. Using multi-tenant, it'll happen very, very quickly. And snapshot cloning is extremely fast, just literally a matter of seconds, even for very big databases. So there's a great agility leap because of these performance advantages. In fact, this provisioning capability is so important. We work very hard on it. There are all sorts of cloning options. You can take a local clone, which is a clone of a PDB in the same CDB that you're in. You can take a remote clone, which is a clone of a PDB in a remote CDB. You can even clone a non-CDB. It's a good way of adopting a PDB, adopting a non-CDB as a PDB. And then we've got this snapshotting capability that I've just been describing. Okay, so the business now has all of these different, these various underlying technologies to take advantage of to support their own agile requirements. And classic stuff here when we're going through what I think of the four gears of a development cycle. You start with development, you do a little bit of user acceptance testing. From there, you go ahead and do some performance, scalability, and reliability testing, PSR, and then you move into production. So it's like shifting through the gears in an old style 4x4 roaster, that sort of thing. We can do all of that using the technologies that I've just been describing. So for example, we might use what I call this hot cloning capability to clone a production database. Here we have a CDB in production, perhaps that's on premises. Maybe your first trial of the cloud would be to have a development environment which shadows this production environment so that you can debug things that happen in production. So you take a clone of this production database. You'd want to be able to do that, of course, without taking it offline, and we support that. That's why we call it a hot clone. It's taken while this database is open read write because transactions are ongoing. And now we have a great source for development teams to take snapshot clones. You see me using all these different technologies I've just been describing here. Snapshot clones in which individual developers can now work on copies of this production database. Very efficient. It allows you to have, to work on problems in parallel. Now, the problem with this sort of setup is that this environment will tend to go stale over time. But have no fear. You have the ability to create what we call a refreshable clone. So the best practice here is to keep these these development copies of production as what we call a refreshable clone, so that you take your initial clone and then you can top it up repeatedly with the incremental transactions that have happened since last time. So developers can always work on a very fresh copy. So when you get those elusive data-dependent bugs or date-dependent bugs, you're working on a fresh set of data all the time. And that makes your development organization very agile when they're addressing the needs of production. Now, switching themes a little bit here from development to production itself, and returning to one of the topics I raised at the very beginning, what about load balancing? And load balancing is a very difficult topic because you run the risk of falling between two stools. On the one hand, you've got the service level agreement, which talks about performance. On the other hand, you've got the service level agreement, which talks about availability. And if you're in danger of violating your performance SLA, you might think, well, let's just move to a server with more horsepower. But if moving to that server involves an outage, you violated your availability SLA. So what we need is the ability to do a relocation to a server with more horsepower without taking an outage in the production system. And we've built this. We call this online PDB relocation. I drew this slide quite carefully, so pay attention. So here are our production users using this CRM system. And what happens is when you do a relocation, we start the cloning process, but we keep people plugged in here. Only when the clone is finished do we switch them over. So there's very little, there's negligible detectable outage for any of these guys, but we've achieved a relocation. So we've kept both the performance and the availability components of the SLA intact. So it's a great example of agility. Now there's a whole topic here that I thought I'd have time to talk about, and I don't think I will. Snapshot carousel. I've got some good videos about this stuff, but I've spent most of this session already talking about agility, and it would be remiss of me in a session that's entitled Best Practices for Isolation and Agility, not to talk about isolation. So I want to talk about isolation now. Big topic. And we have a comprehensive architecture to handle isolation. We've got comprehensive resource management built into the database. Now, resource management needs to consider all of these various, what I call the dimensions of computing. There's CPU, there's memory, parallel execution servers, storage, sessions, IOPS, all of these things. So these are the various dimensions of computing. And Resource Manager allows us to control every one of these things. Because if you imagine an enormous Exadata machine, these days I can't even remember how many CPUs we've got in one of these full racks. It's hundreds of them. Individual workloads don't need to have full reign of that system. Indeed, in a cloud-based system, which is our best practice, you get what you pay for. That's a very good model. You get what you pay for. So for example, again, I'll point back to Autonomous Database. When you provision one of these things, it says, how many CPUs do you want? You say, I don't know, I'll have 4. Now we have auto scaling, that's a different story. But think of 4 as just a basic limit. So I've got 4 CPUs. That's the maximum I can use. And now, if I want to use more, I just dial it up a little bit. We'll give you more CPUs. But Resource Manager is how we implement that limit. And we have resource management capabilities to restrict consumption of every one of these dimensions. So Resource Manager is your best practice. Your best practice is to use Resource Manager in a get what you pay for model. So we've got instant scalability, you have clear cost allocation, and the best practice is to index things from just a few little, a few major controls. So rather than giving you all sorts of knobs and buttons to twiddle and push, just give you 2. This is what we do in Autonomous Database. You control your number of CPUs and your storage, and everything else is dependent and indexed from that. So that's very important. Now, this is the get what you pay for capability, but there's more than this to isolation. A lot of people talk in terms of noisy neighbors. You get all these benefits of consolidation. We've talked about efficiency. We've talked about agility, but you don't want to suffer from somebody who comes along and throws an enormous inefficient query at the system and sucks all the resources away from you so that just when you need your resources, they're not available. Well, Resource Manager can limit that guy and you get what you pay for. He can't take what you've paid for. So this controls your degree of resource over allocation. You can have no resource over allocation, or you can control that degree of over allocation, because typically your system won't be 100% used. A general consolidation proposition is the more workloads you consolidate, the less likely it is that they all come to peak at the same time. So you can over allocate to some extent, and everybody still gets what they need when they need it. And then the most extreme example of the need to use resource management is to prevent the malicious actors, the denial of service situation, because everybody is constrained to within their own PDB, and we have resource management on all of these cases, so we've got great isolation. So here we are with a very good proposition for delivering isolation and agility. It's multi-tenant. How do you upgrade? It's really easy. It's as easy as 1, 2, 3. The first step is you upgrade all of your old databases, the non-CDBs, upgrade them to the latest version. That's 21C these days, or perhaps 19C if you're upgrading your production databases. That's where you should be aiming. You adopt them as PDB. So basically create a CDB and you plug them in. And step 3 is that you upgrade your applications to work with multi-tenant. But wait, since the applications run unchanged, there is no step 3. My point here, I'm being a little glib. It's very easy to upgrade to this architecture. And that was really the fourth benefit. So it's extremely efficient technically and operationally. You've got this fantastic agility, and it's easy. It's easy to adopt and it's easy to use. So let's talk quickly about use cases, and then we'll have a few minutes for Q&A. Now, this is the only architecture of Oracle database from 21C onwards. In 19C, you have the choice of non-CDBs or multi-tenant, but from 21C and onwards, only multi-tenant. So by definition, we have to support all use cases of Oracle database. But 3 prominent ones are these: development and testing, enterprise consolidation, and software as a service, which I mentioned earlier. So in development and testing, we've got so many features that are extremely valuable. Here, I think the name of the game is agility. Fast provisioning and cloning, unplugging and plugging of databases, refreshable PDBs. You can mask your data if you want to. And we have this capability snapshot carousel that I didn't have enough time to talk to you about. Now in production, you've got a different set of requirements here. In production, you get the efficiencies by consolidating at high scale, and 4K is plenty of PDBs. 252 is plenty of PDBs to get some tremendous ROI, return on investment, from multi-tenant. You hear we're getting benefits because we can manage many as one. We've got comprehensive isolation, our other big theme today, and online tenant relocation allows us the agility to balance loads very, very efficiently. In software as a service, we've got an instant SaaS architecture. Applications run unchanged. We talked about common application objects at the beginning, and this capability of location transparency, which allows us to move things away very confidently, move things around very confidently for load balancing purposes, the sort of thing we need agility for. So there are lots more use cases here, and a very large number of customers is just a snapshot of some who've allowed us to use their logos, who are successfully using multi-tenant to do a very wide range of things in this environment. Of course, we're using it a great deal internally. I keep talking about autonomous database because that's my other job here. It's fantastic. We're using a great deal in SaaS, in Fusion, in NetSuite, where we now have 23 or 24,000 tenants, each running their own PDB. It's a major upgrade. Why would the people that invented SaaS upgrade to our environment? Because of agility and because of isolation. Lots of our old applications and lots of our new stuff as well. The list is too long to put on a single slide. So summarizing here, this is the architecture of multi-tenant. We have these self-contained pluggable databases for each application, in which applications run unchanged. The PDBs can be rapidly provisioned by this process called cloning. And a pluggable database is a portable database. We've talked about all the agility benefits of portability here. Common operations are performed at the CDB level, so you can manage many as one. This is where you get the operational efficiency. So things like upgrades, HA backup, we do these at the CDB level, but we retain granular control when appropriate, granular agility, granular isolation. And the technical efficiencies come because we have this shared operating environment, shared set of memory, shared set of background processes. So by eliminating these redundant replications of overheads that you get with things like VMs or things like Docker containers with databases running inside them, by eliminating that redundant replication of overheads, we leave more processing available for the workloads. So you get more applications per server. So this is a summary of the benefits that multi-tenant delivers. You minimize capital expenses because we can get more applications per server, and we minimize operating expenses because you can manage many as one. We maximize agility with all of the examples that I've been talking about for the last half hour or so. And it's easy. It's easy to adopt because applications run unchanged, and it's easy to use because the interface is SQL. You already know how to use this.